you deal with three types of fields in detail in your A-level. Masses have gravitational fields around them and thereby exert gravitational forces on other masses. Charges have electric fields around them and thereby exert electrostatic forces on other charges. And moving charges have magnetic fields around them and thereby exert magnetic forces on other moving charges. Remember that current-carrying wires contain moving charges, so these have magnetic fields around them. Also remember that magnets exert magnetic forces, but you don't need to know why for your A-level, so we won't discuss it here. The field strengths for the different fields are shown here. The gravitational field strength is the force per unit mass, the electric field strength is the force per unit charge, and the magnetic field strength is the force per unit current per unit length on a current-carrying wire perpendicular to the field. Now, I've just called B the magnetic field strength, and it is totally okay for you to think of B as the magnetic field strength for your A-level. However, you must call it the magnetic flux density. If you really want to know why, keep listening now, otherwise just mute the video until you see the next title. So in fact, it turns out there are two types of magnetic field. One of them is called the B field and one of them is called the H field. And the H field got the name magnetic field strength first, and so the strength of the B field had to be given a different name, and that's why it ended up with magnetic flux density. The direction of a magnetic field is shown by the arrows on the field lines, and it's from north to south, which is the direction another north pole will be pushed. Round a bar magnet, they look like this. Between the poles of a horseshoe magnet, they look like this. And around a current-carrying wire, they are shown by the direction of your fingers in the right-hand corkscrew rule. The direction of your thumb shows the direction of the current. Remember, that's the direction positive charge is flowing. And the direction of your fingers shows the direction of the magnetic field. This means that the field lines around a current-carrying wire form concentric circles, and the field lines around a coil of wire, which we call a solenoid, look like those around a bar magnet. When we want to draw a magnetic field coming out of the page, we represent that with a dot, and going into the page we represent with a cross in a circle. This is meant to look like the point of an arrow coming towards you, or the feathers of the arrow as it goes away from you. Remember that a uniform field is one where the field lines are parallel and evenly spaced. If you want an approximately uniform magnetic field for an experiment, you can use the field between the poles of a horseshoe magnet, or between the North Pole and the South Pole of two different magnets, or the field inside a coil is also approximately uniform. So often if we want an approximately uniform magnetic field for an experiment, we use large flat coils called Helmholtz coils that are about 10 centimetres across, and this gives quite a large area in which the field is approximately uniform.